Let's continue.
Yeah.
Well,
When I was
yeah, I mean the model.
all right. When I was for today.
Oh, guys, it's going to infinity.
Whoa.
Whoa.
There's so many.
I don't like it.
Ideal way to make
So today we will be talking about once you have your pipeline set up, how to try and improve your model results. That's going to be the start. And I'll try to transition into a bit of an outlook of some slightly more advanced techniques that people have proposed. It's going to be a bit dense again, like a lot of content, but especially towards the second half, it's really more kind of here's a bit of an outlook, see what can be done. Not all of those is going to be valid and useful for every one of you, but if I include every one of you, would be that you will be here tomorrow again, just in lecture. So I'll just pick out some parts that may or hopefully are interesting for you. Works, there we go. So let's just quick recap on the 3 splits that we made.
But
Yes.
before you get started, do you mind moving the laptop so that you're not behind it, because it's really distracting because you're like moving like 10 times.
This one. This, whatever.
Sorry, I can concentrate on what I'm saying.
This is pretty pointless, whatever.
Thank you.
So let's recap the splits that we made. Again, this is useful and this is important for every kind of statistical data-driven pipeline. We have the training set where we just fit the model to the data. The validation set we have so far used to just optimize the hyperparameters, as I've said in the previous lecture. But this also implies that we want to test the generalization of the model. How well does it perform beyond the training set? And this is going to be very important for basically all of you. And the test set we don't touch until the very end, where we have a model that we're happy with, and then we try out for real how the model performs. So we don't use this for parameter tuning, neither parameter nor hyperparameter, because that would be cheating. And I want to get into this generalization a little bit. And tell me if this is probably not new, but just as a recap, I can speed up a bit. What we want to do is over the epochs of training, so iteration of the full data set, we want to plot those, for example, during training. So if something like this happens, some of you might be already at that stage, I'm not sure. That basically means that your model trains. So great, yes, but that doesn't mean anything at all about whether your model performs well or not. It just means that it basically fits your training data. And then the important part is, which is why we have the validation set, we want to plot that as well. This could look a bit like this. And who can tell me what's happening here? What's the term for this effect? Overfitting. Exactly, thank you. Overfitting. So this basically means we overfit the training set because the validation performance is just subpar. That is not so horrible overfitting. It depends on the scale of the loss, but it is because there is a gap. This can also happen, especially with deep learning, that the validation loss goes down with the model fairly well, and at some point it starts to increase again, or it starts to stabilize. That's also overfitting. And that's basically very simple to fix. Just stop before this happens. And some might be at this stage where just the validation doesn't decrease at all. Of course, that's also overfitting, but it could also be an error. And then some might have experience, or some might experience something like this. And that's not necessarily overfitting, that's just unstable training. So, but all of these can happen, especially with deep learning. And let's see what overfitting actually looks like, just again for a recap. This time we're not plotting the loss against the epochs, we're plotting 2 inputs to the model, x1 and x2. You can call them features, you can call them covariates, inputs to the model. Assume it's just a 2-dimensional problem. And of course you can imagine that this seems like a reasonable, like a good fit, because it kind of matches the distribution of our data. And if you have the validation point in blue, it's not so far off from the curve, but it is a bit off. There is a bit of an error in quotes. And overfitting could look something like this. right? So we have a perfect loss in training. All the orange points are met, no loss there. But the validation loss is going to be huge. And that's exactly what happens with overfitting. So in this case, for example, classical non-deep learning, it happens because we fit a polynomial that has too many degrees of freedom. So this polynomial is like, I don't know how many orders this is, I just drew this by hand. But compared to the quadratic polynomial we had before, this one has, say, too many parameters. And the parameters are too big. The values are too big, so it can fit every point. So if there's too many parameters, you can overfit your data. Yes.
Does this become like more of an issue in deep learning? Like, does overfitting become a risk linearly with like the number of layers?
Okay, I wanted to ask, what is the obvious next question? You took it away.
Oh.
So deep learning models have millions, sometimes billions of parameters. So is that a problem? The intuitive answer would be yes. The real answer is actually no. So for some reason, deep learning models, if you add more layers, more parameters, they don't really overfit just because of that. And the reason for that is no one knows. Well, you can add regularization. I'm going to go into regularization. You can regularize deep learning models, and deep learning models can overfit like crazy. But the effect of adding more parameters, more layers, bigger weights, whatever, doesn't automatically lead to overfit. And it's one of the many mysteries of deep learning that no one knows why. They're trying to investigate that at the moment. Maybe they found it out, but I haven't seen anything. And just for completeness, I guess you're with me, that is called underfitting. And with deep learning, you almost never have this problem because they have so many parameters that if they underfit, it's a bug in your code, usually. Yes, exactly. So again, recap. If this phenomenon, validation loss, doesn't go down at all, check if your hyperparameters are obviously wrong. Like if you have a learning rate of 10,000, it's not going to work. And check your code for errors, because most likely you have some problem that your loss just turns to 0 all the time or whatever. This can happen. Make the usual sanity checks, plot everything, debug the loss, etc. If this happens, we're going to apply some tricks against that. I can't go through all of them, but just some examples. We're going to cover that. Also with this one, it's the same. And you can do what's called early stopping. So when you train over the epochs, you plot the loss, train a validation at each epoch. And when this starts to happen, you just pick the last epoch before this starts to happen. This is going to be your final one. It's a bit of a hacky trick, but it works. And then finally, when this happens, you can increase the batch size. Very often this is because the gradients are too small, so the model just meanders about. But if you increase the batch size, you can streamline the gradient so that it doesn't jitter about. You could perform what's called gradient clipping, so you limit the limit the gradients to an upper and lower ceiling. That's a bit hacky. Most often, this is actually not a big problem. So this could look very bad if you have giant spikes. Try the batch size trick. Check for the usual things. But otherwise, you can live with it. It can be pretty nice.
Is it ever a sign of noisy data?
Could also be, exactly. Yes. Yes.
Is the orange line the training or the blue line the training?
Or in this case, orange is training, blue is validation.
I have the
But
opposite.
this effect can happen with both training and validation.
Okay, yeah.
Is it?
Does the learning rate, like how far it's stepping through that space, have any effect on how stable these curves are?
A learning rate, not so much usually. At the beginning, it could be because the gradients are still strong and the parameters are still a bit random. But especially if you pre-train, if you start from ImageNet, for example, it's not really that much of an effect of the learning rate. It's more if we have small batches, very heterogeneous data sets, noisy labels, these kind of things that can cause that. Okay. It's a bit random actually. Anyway.
Does it ever stabilize over time? Like, would that line, if it starts like that, does it continue like that, or could it stabilize?
This really depends on your data set and on your model. Sometimes it does. I've seen everything. I've seen it not doing that at all, I've seen never stabilizing, I've seen stabilizing. It's a bit unpredictable.
Is it a problem, like if it does stabilize, is that okay as long as it stabilizes later on?
If it stabilizes, it's okay, unless it stabilizes in a bad state where it
Yeah.
overfits. So that can just a warning. This can happen. You can address it with the batch size a bit, do some pre-flight checks. But if it happens and it still learns, not a big deal. So and let's get into some tricks. But always this applies no matter what. Check your data. Check if it's valid. Ensure that the data set is representative. If you train on just a subpart of your actual data distribution, the model is not going to learn the rest. Ensure that the splits are equally representative. So you want to include all the representation in the training set and in the test set, because otherwise you're going to introduce biases. Either the model is going to be bad or your test is not going to be representative. Make sure to remove autocorrelation. So for example, temporal autocorrelation or spatial, like two neighboring samples sharing characteristics because they are close to each other. Make sure to eliminate that as much as possible, and especially spillage across splits. So if you use a convolutional neural network, never do spatial random sampling because you're going to have neighboring effects. And then again, just in general, biases is a bit of a repetitive thing, but it's really what creeps in all the time. Avoid biases. And sometimes they can be really, really nasty. It can be very much hidden. You wonder why your model predicts something. Could be something harmless, like it misses a species. It could be something really bad, like it makes politically incorrect statements because you have some bias implicit in the data. All happened. Can be really bad. Good. Let's start with some run-of-the-mill tricks. These are the ones that apply to almost everyone. Weight decay, scheduling the learning rate, batch normalization, dropout, and this is what Björn is going to talk about tomorrow, data augmentation. So I will not go into this, but everyone should use data augmentation. We'll see that tomorrow. Let's start with weight decay. So last equation, very simple. This is the objectives that we want to solve. So this theta is the model parameters. These are the ones the model learns. And basically, this is a gradient step. This is what stochastic gradient descent in its bare form does. So we say the model parameters at step t plus 1 is the current parameters at step t minus the eta, which is the learning rate, times the gradients. So again, you have the gradients of the loss function L with respect to the model parameters and the current. And this is the learning rate. And there is this minus there because when you calculate the gradient, we want to go down. Very simple. So that basically does our parameter update. And now what we're going to do is we add a second term, which is this. And what is this? So we have a lambda, and we have the sum of squares of our model parameters. And yeah,
Keep going.
it's actually a bit well, it's not 100% correct, but it's just kind of, yeah, you want to minimize that. And the idea is, I'm going to update the slides later, but you want to minimize this part. So again, that, and this is going to be a weight decay. So why would you want to minimize the parameters of the model?
You can have like parameters that just get, like if you have like opposite parameters, then one can get really big and one can get really like negative, and then they can just shoot off in opposite directions.
Exactly, yeah. That's what we've seen before when we went through this random fancy squiggly line. This only happens if your parameters are enormous. With deep learning, it's the same.
So is that like the same idea as something like ridge regression, where you're like minimizing that?
It's very common, yeah. It's very, very similar. Also, if you've heard of, for example, Lasso regularization, that is actually the absolute difference. That's the L1 norm.
So
This
that would
is
just be if
the
you
norm.
took the squared and made it, just you took that off.
Yeah, exactly. So I have to update the slides. This is not exactly correct. You don't add it to the parameters. You minimize that as is part of those. So stay tuned. The stories you want to keep the model parameters at a minimum. And this is called weight decay. So you decay the weights with every step a little bit, so you shrink them a little bit, so that they don't become too big, they don't overfit. And in practice, it's just one parameter. You add this to the optimizer like this, and you have to again. It's another hyperparameter. You have to play around with it. I found personally sometimes 10 to the power of -3 is a good start. Sometimes some projects actually work better without it, and some work better with a stronger or weight decay. But this is something you want to play around if you experience overfitting. Next, learning rate scheduling. So basically, once you start training, at some point, let's say there, the model will have learned the basics of your data set, and it will start to focus on very subtle details in its quest to always minimize the loss as much as possible. And in doing so, it will take finer and finer steps, because at some point, it might predict the correct species with like 80% of confidence, but it really is encouraged to push to 100%. So we'll start to really dig down on the very subtle details of the input. And for that, it needs to take smaller gradient steps. And of course, what we do is we reduce the learning rate over time. The learning rate is what scales the magnitude of the gradients that we apply to the parameters. And again, this might look a bit like this. For example, if you do manual steps, so over time, your models, the loss might start to stagnate, and then if you reduce the learning rate, you will see that it goes down again, and then maybe again. But this is stepwise learning rate. There's multiple options of doing that. Again, it's all built into PyTorch. But let's look. So what you can do is you can import a learning rate scheduler, which obviously schedules the learning rate. And then the first one is what we've just seen, is called step LR. It's just basically this one, again, has some parameters. You give it the optimizer, and in this case, a step size of 10 and a gamma of 0.1, which means every 10 epochs, it multiplies the learning rate by 0.1. So train for 10 epochs, then you give a learning rate of 0.01, then the next 10 epochs is going to be 0.001, you get it. There's also the equivalent of a multi-step LR, which allows you to specify exactly when you want to apply the reduction. So here I'm going to say I want to reduce at epochs 3, 15, and 25, each time reducing by a factor of 10. But these are hard-coded ones. And what you can also do is this is called reduce learning rate on plateau, which basically takes in a quantity that you define, for example, the validation loss, and monitors this. And it checks that if the validation loss hasn't decreased for a certain number of epochs, it applies the reduction. It's a bit controversial. Some people swear by this. I personally never use it, but it could be useful because then you don't have to worry in that it automatically monitors the learning rate. It monitors the loss, but it can apply it semi-arbitrarily. So you still need to keep an eye out on what this thing does. But some people use it and it can work. Yes.
Is there a trade-off for if you're decreasing the learning rate and it's focusing on finer and finer details, is that always better, or is there ever a risk that the model would get like stuck on the wrong tiny features?
Very good question. Again, this depends on the setup and on your preferences. So there's all kinds of tricks people have done. For example, some people, what I sometimes do is I start with a small learning rate and I just actually keep that fixed. Then it takes longer, but it sometimes reaches a better optimum. Some people start with a slow one, ramp it up, and then degrade again the learning rate to kind of, it's called warm starting. And the classic approach is you start with a relatively high one, like 0.01, and you reduce it over time. It's really, again, typical deep learning. It's unpredictable what this does on your project. It's really, we don't know. But some depending on what it is, you might have to experiment a little bit. But again, personal tip, don't experiment too much, because at some point you're going to be lost in a million experiments trying to just tweak out a little bit more percentage, and it's going to become a mess. So at some point, take a reasonable guess, play around a little bit, but once you get somewhere that you think it starts to get training well and it doesn't overfit too much, stick with the hyperparameters and focus on the stuff around. But if you want to use one of those schedulers, it's very simple in practice. Let's say you have your training loop, like define your model, define the optimizer, you define an additional scheduler, which takes the optimizer input. Here we're going to take the simple step LR. You iterate over your epochs and you have a train and a validate function. And then at the end, it just calls scheduler.spec. So this is when the scheduler iterates. So in this case, if we do this 10 times for 10 epochs, then it's going to reduce the learn. For the reduce LR on plateau, it's a bit different because then you give it a quantity. In this case, I'm giving it the validation loss so that it has something to estimate whether this is plateauing or not. But otherwise, it's exactly the same principle. Good. Let's go to the next one. Batch norm. Batch normalization is an extra layer in deep learning models. It is probably already built into what you're using. If you use ResNet 50, for example, batch norm is built in. If you use RetiNet, it's also built in. I'm just going to explain what this does. So you might have heard that your data normalization is very important because your data can have very arbitrary values, right? They can spread along. So in regular images, for example, it's just values between 0 and 255. But if you don't normalize them, then it becomes difficult for the model. So for example, if your average value is not 0, then the model has to add a bias so that it can compensate for this. And now you have an example where you have the land surface temperature in Kelvin. So your average temperature, your average value is like 270 something, right? And if you feed that value to a deep learning model, it has to have extreme high weights because it has to bring its parameters into the 270-80 range. And remember, with weight decay, we cannot do that. So we have weight decay, which tries to put our parameters down, and we have the input values which are high so that they require high parameters. It's never going to work, which is why you need to normalize your data. So you want to zero center it and make it to unit variance. So you subtract the mean and you divide by the standard deviation. That's for the input. Intermediate model outputs can drift because your layers, they do all sorts of operations. So wouldn't it be great if we could normalize the intermediate model tensors to unit norm, to zero norm and unit variance? That's what batch norm does. So here's how this works. During training, we take a batch of images. Okay, we take our data points and we feed this through, for example, a convolutional layer that's part of your model. And then this gives you an output tensor that's somewhere in the middle of your model, right after the conv layer. And now we want to normalize this tensor. So what we do is we calculate over this batch the mean and standard deviation values of this tensor. We apply this, and then importantly, we store these values internally in the layer, in the model. So we basically create a running average. We create running statistics. We iterate over our data set, and we accumulate the mean and standard deviation values, and we continuously update those with the training batches. Then, of course, we have the next layer. We could add another batch norm after the next conv, for example. It's a bit, where we have batch norm. And then during inference or testing, we don't always have the same batch size. And also, we don't want to make our model predictions dependent on the batch statistics of the test images. But what we do instead then, if we have this same tensor, we normalize those with the learned statistics from the training set. So that basically, again, this is not biased by our test set, but it is informed by our training batches. This is basically what batch normalization does. Again, it's probably built into the model we already have. Just interesting to know. But this, of course, what batch norm does, it doesn't necessarily prevent overfitting, but it actually makes training models at scale possible. Many models don't work at all without batch norm.
Quick question.
Yes.
Does this take into consideration the normalization you did before you import your data, for example?
So only implicitly, because what this does is it calculates its own normalization parameters of the intermediate tensor in the model.
Gotcha. Okay.
You cannot fix those in advance because as your model learns, these statistics change, right? So if you change the filter weights of this conv1 layer, the mean and standard deviation values change. So that's why what they do is they have this exponentially decaying average over the training images.
Cool. And just a follow-up question, we had a little discussion in our group yesterday about the difference between standardization and normalization. And do you use the two terms interchangeably here?
So I can't give you a definitive answer.
Okay.
I mean, I often only use the term normalization. It could mean something different, I guess.
Usually when I use the term standardization, it implies like getting a bunch of data sources from different people and making sure that they basically are all mapped into the same format. But that format is less about normalizing them and more about like making sure that like every single data point has access to the same like information. So if you have like time, they're all in the same like date time format and every single image has time associated. That's what I think about in terms of the data standardization. Normalization for me is like explicitly this type of thing. And I've never used standardization to mean normalization. But I don't know, that's just
We do in the college.
Yeah.
Yeah, we do in the college, like, well, we use it to mean the same thing. Like if you standardize your data, you normalize it,
That's so interesting.
feed it into models and things.
I think sometimes people use it to refer, like some people say, oh, standardization, subtract the mean off. And some people might use that as subtract the mean off and divide by the standard deviation. So I think that's for me, like, that's
Yeah.
where it comes from in ecology.
I think we also looped in the word scaling. And then normalization versus scaling, whereas with scaling, we refer to as like a min-max scaling, like we kind of just compress our data to like a 0 to 1 range, whereas normalization makes it to be 0 mean unit variance. I think here we're talking about normalization and not about scaling.
That's true. So scaling is, for example, automatically done when you call the two tensor function. It scales if you have an 8-bit image. It scales it from 0 to 255 to 0 to 1, because that's again what's more convenient for people.
How do you know if you do batch normalization? Do you look at the weights of each layer and say like, oh, these are very large, I should batch normalize?
You could probably do that, but most people, because that's kind of cumbersome, they just try. I mean, there's some standard sequences of layers that people use. For example, it could be batch norm conv and then a nonlinear activation function. So they just stick with one of those and apply it one by one. Usually it only makes sense to apply batch norm around a layer that learns its own weights. So for example, convolution. If you have something like pooling that doesn't have its own weights, then it doesn't make sense to use batch norm. We can talk about building blocks of neural networks, actually we should, but let's see if time permits, yeah. So the next trick is dropout. Now, dropout is not necessarily in your model. It's something you can add, and it can work wonders, or it's not. Again, it's not guaranteed. What dropout does is the following. Let's say you have your model, you have your layers, conv1, etc. And at the end, what you have is what's called maybe a fully connected layer, which gives you the output class. In this case, cat or dog. Now, what dropout does is it just disables some of your neurons in your layer. So if you add dropout after a certain fully connected layer, and you can specify the percentage or the probability. For example, if you have dropout with a probability of 20%, it will shut off 20% of randomly picked outputs. And then it just becomes 0, so the model has no chance of going there. And every forward pass, it eliminates a different set of 20% of the. Now, Why would this be useful?
So the model doesn't depend on one specific weight.
Huh?
We can just go through that one all the time.
Exactly. And what was the problem with that? Yeah, that's the effect, yeah. So the story is, this is a very similar concept to what also applied in random forests. Because you have what's called an ensemble. So in a random forest, every decision tree is a weak learner. It knows a little bit about certain parts of your data, but it cannot generalize. But because of that, it doesn't overfit. Otherwise, it could go forever until it can map its training set perfectly. But because it knows just a little bit, and there's hundreds of them, if you average them, they are a strong ensemble. Here it's exactly the same. We artificially disable parts of the model so that it is forced to find alternate pathways. And with that, it has to make compromises. So this prevents the model from overfitting through the training set. And this works during training. You turn off a random percent of neurons. During testing, you turn off dropout. You just use everything. So that's why when in my code I had this model.train and model.eval, that .eval puts the model into evaluation mode. So it switches the batch norm to use the learn statistics, and it switches off dropout, for example. That's why this code is there. So dropout is very simple. It's an extra layer. You specify the percentage, and then you see whether it works or not. Good. So now let's go into some advanced tricks, because I mean these are some stuff you could use, but they might not help because sometimes your data just misbehaves. Actually, that's the norm in real life data. So what can we do? And there's a ton here, and what I want to make clear now is this is far from exhaustive. There's a million more things people have done, and not all of these apply to all of you. Some might have none of these problems at all. So you might find one, maybe two in here that is or could be useful for you. And as we move along, some of them become a little bit esoteric. And these are just things people tried. So it doesn't matter if you don't memorize all of the stuff I'm telling you here. It's just kind of a little bit of a reference and a bit of an interesting insight into what's next, what people have done beyond the typical classification pipeline. So let's start with something that most of you are affected by, which is class imbalance. And there's a couple of things you can do. Again, far from exhaustive, just some very simple things you might want to try. Now, imbalance could be multiple things. If you just could be, for example, you have just two classes. Casey has the problem. He has a background and a walrus class. And the background class is millions of pixels in remote sensing images, and the walrus is just a couple thousand. So you have this huge imbalance with just two classes. What it can also be is the infamous long tail, when you have many classes and the majority of them occurs in very low frequencies. This is from the iNaturalist dataset, by the way. We see we have these few classes like Danos Plexipus, the butterfly, which occurs in huge numbers, and we have a lot of classes where you find almost no examples at all because they just more cryptic, or people are not interested in them. Again, biases. That's a bias. So we're going to combat this. But before you even think about what to do here, you need to do some pre-flight checks. Check the tail. Like, how many samples do you actually have? I've recently had a data set where 10,000 species had less than 3 training images. What do? You can't train a deep learning model on that. Then check the imbalance. Like, how severe is the imbalance actually? If it is 1 to a million, you might have a bit more trouble than if it's 1 to 200, for example. And very importantly, check the test set, because and this together also with what Eli said, check the accuracy metrics. So we've seen the lecture on accuracy evaluation, and these together, they play an important role. So if, for example, your test set is equally imbalanced, which is the case in, again, the real world, and you use overall accuracy as an evaluation metric, you best leave the long tail as it is, because the overall accuracy is going to say if you predict the majority classes perfectly, and you can mispredict all the tail, doesn't matter, maybe 10% worse. It's not a big deal. So if your accuracy metric is biased by the number of samples per class, then you want to be careful. Otherwise, you want to take a better accuracy metric, like, I don't know, average accuracy, or you want to check precision per class, precision and recall, mean average precision, these kind of things. And again, check the test set. In the iNaturalist contest, the test set is artificially balanced. In your data set, which is not a benchmark, this is likely not true. Your test data set is probably as imbalanced as the training set. Then, also important to check your objective. How important are the tail classes for you? Do you need to find the needle in the haystack? Daisy, for example, has because the walruses are important to find. So these are all things, considerations you have to think about before even thinking about tackling the long term. But once you have that, there's a couple of things you do. I mean, for example, something like that. That's a paper from this year, from a computer vision conference, CVPR, where they claim to have solved the long tail. And you don't need to memorize this, because I've read the paper, I still don't fully understand how this works. So long message here is you can go crazy, but very often this doesn't really work. And this worked for their data set, but it doesn't generalize very well usually. But there's much, so the sad reality is this: you can almost never solve the law. That's kind of my opinion. It's very hard to solve it, but you can at least counteract it a little bit. So, and to do that, there's some very simple things. The first one is loss weighting. So you see here, we have in the middle this classical cross entropy loss, which is for classification. And by default, this treats every label class equally. But what we can do is we can, for example, create a histogram of our training set. And we can flip that and maybe square it, whatever. So we can say we give more importance to those classes, species that have less training samples. So we increase the gradients for the rare classes and we reduce them for the common classes. That's what loss weighting does. Whether or not this is going to lead to a better model, again, nobody knows. You have to try it. It might not have such a great effect after all, but sometimes I found this to work reasonably well. So for Casey, for example, you want to try that maybe. Then you can have custom loss functions. So for the regression people among us, there is something called, for example, focal loss. And I'm saying this is built into RetinaNet, which is an object detector. They use this to regress the bounding boxes, but you can use it to regress your own stuff. And this looks like this. What this does is, you see here, what it does is it modulates the gradients based on the model confidence. You see the actual loss in the y-axis and the probability in the x-axis. So what you see there at the tail end is a well-classified examples. So these are examples where the model is really confident that it is the certain class you want to do, the species you're looking for. And these are actually well classified. So the loss is 0, which means that the model is correct. So if the model is already correct and it only assigns 80% confidence, you don't want it to hammer it down to 100%, because then it would just focus on the well classified examples and ignore the rest. So what you want to do is you want to reduce the loss weight for when the model is correct and sufficiently confident. That's called the focal loss. And again, this is built into RetinaNet. It's actually for the classification part. So that's something you might want to try. It's built in there. You can also use this for regular classification. You're going to find implementations on GitHub if you do carefully. This can help. Then another one which I'm a big fan of, again, sometimes it works, sometimes it doesn't, is called curriculum learning. This is inspired by how humans learn, that you start with something simple and you gradually make the objective more difficult. It's what Ben Weinstein talked about yesterday. That's why pre-training is important. You don't want to have the model to learn every concept since Adam and Eve again. So this, again, there is no there's no obvious recipe for this, but what I, for example, do is if I have an imbalanced data set, I start by subsampling. I throw away the majority of the head end of the classes, and I artificially balance the data set. Of course, with that you remove a lot of the data you have, but you do this only for one epoch, and then for the next epoch you resample, and then you slightly increase until you reach the full data set. So in the beginning, you subsample so that the model puts equal importance to the tail classes. And I found this sometimes it can work phenomenally, but careful, sometimes it can lead to massive overfitting as well. So worth a try if you have strong imbalance, not guaranteed to work. It's going to be the leitmotif of this lecture. Yes.
So would this be, so for a problem like mine where I have many classes and like, you know, I have a long tail problem basically, would this be, like, would I then introduce, like, would I start with my most populated classes and then slowly introduce my rarer classes? Is that what you're saying, sir?
It's more the other way around. So
Okay.
you have your long tail,
Sure.
you cut off the head end. So you take those classes which are most representative and limit their numbers. And say, for example, you start if your tail end you have a class with only 50 images. You could say for each class you take a random subset of at most 50 or 100 images.
Sure.
So you really cut them off. And then the next epoch you can say you do that again, but you sample a new random set or a new random one. And then at some point you say, instead of 50 images, now I take 100, and I take 200, 500. So you gradually increase.
Okay.
I found this to work rather well. Here's another example. I mean, this is a bit of an artificial one. If you have different sized bounding boxes, you might want to start with the big ones, add the small ones later, or the other way around, depending on the difficulty. It's the way of gradually increasing complexity to the model as it moves along in training. The first example is really what I found this to be most useful. Good. So there's more about imbalance we can talk about in detail, but let's move on to domain shifts. So again, not sure how useful for many of you. Probably not for a lot, but we can talk about that. Just it's an interesting concept. In shift is this really like you have the same task, for example, but for completely different types of images. So on the left we have an African savanna, and on the right we have the same for animal detection, but it's in a salt pan or a gravel pan actually. So you can imagine if you train a model on images from the left, it's not going to perform on the right because it has never seen this data. Us humans have no problem. We see the animals in both, but that's because our brain is informed by years of learning from auxiliary tasks that the model just doesn't have. And also our brains are far more advanced than neural networks, artificial neural networks. So a model cannot do this, but we can do stuff to counteract this problem. So a very typical domain adaptation strategy is to adapt the features. So what we do is we have what's called a source model. This is the one where we also have labels, so we can train this, for example, to detect animals. And now we want to transform this to also work on the target domain. So we have our objective loss here, which compares the source prediction, y hat source, with the source labels, y source. And we also have our intermediate features there, this blue tensor, which is, for example, the output of the penultimate layer. Sarah talked about FC7 for reception before. It's usually the second last output of your model, where the image is summarized in a high-dimensional feature vector. So then we want to make this work on the target. So what we do is we copy the model over, and we just apply it. And in the beginning, it's going to give us garbage predictions, right? Because it has never seen images of this domain. So what we can do then, we also have our feature vectors there. We can add a domain loss that tries to align these features. Because in principle, these features at the end of the model should summarize animals in this case, like our objective. They should not really summarize too much the actual colors or whatever you have in the input image. So the further down you go in the model, the more the representation of the outputs of the model, it starts very geometric, and the further down you go, it becomes more semantic. And at some point, close to the end, it should reflect the objective, be it classification, be it detection. It should not really depend on the input image anymore. That's the idea of domain annotation. We try to align these tensors so that they convey the same concept. And many of these domain losses are unsupervised, which means that you don't need target bounding boxes here to train the model. You can, if you have, would be nice, but in principle, this is unsupervised. You just align the features. And there's different losses that have been proposed. Here's just two of them. There's a zillion. You have, for example, deep coral, which is classic. It aligns the covariances of these tensors. Decay, that is one that I kind of messed up myself, which uses a different type of transportation between the features, but they all try to do the same thing, essentially. Yes.
Can you elaborate what you mean by align? Like, is it like if you're looking at animals are the same color between two images? Like, is it like is it feature related or position related or something else?
Yeah, that's a good point. So that's what I said before when we go to our semantics. So what I mean by align is that whenever, for example, these feature tensors are describing an animal, they should be the same, because it's just all the, like here at the end, all the final layer, the classifying layer of your model cares about if it's an animal or not. It doesn't care if the animal is oriented in a strange way or if it's brown instead of white or something. It's just animal. So what you want to do is you want to make these animal representations the same, whether it is the source or the target domain, so that the same classifier can be used for both images. Yes.
But then wouldn't you need to have an identical image in both the source and target domain?
Very good question. So the problem is, because you don't have identical images, the animals can be at different positions, right?
Yeah.
In this case, for classification is not a problem, but for here it is one. So that's where these domain adaptation strategies differ. They try to find correspondences. They try to find which part of the target features correspond to which part of the source features. Because it's not always the same. So if this blue tensor is still spatial, then the simplest you could do is you could just minimize the square error distance of the two. But then it would mean that the top left feature has to correspond to the top left feature in both domains. And if one has an animal, one doesn't, it's not going to work. So what, for example, deep coral does, it just aligns the covariances. The covariances are spatially independent. So it makes sure that the covariances of the tensors are the same, but it doesn't care about which part to match to what. So this, for example, this is a very simple strategy that you don't need to know exactly. You don't need matching pairs. The second one uses a bit of a more complicated scenario where it tries to calculate the distances between the tensors in terms of histogram distributions, and it tries to find the optimal pathways. You can make this all very fancy. You can also transfer across images in a batch. It can make it arbitrarily complex, but the idea is basically, if the assumption here is that the two domains are not too different from each other, that the model generally gets it right even in target. That you can, if you find correspondences, which part of the source corresponds to which part of the target. If you do that well, you can align those features. You can make them similar so that the classifier works in both. Yes.
One more question, sorry. So the source model and the target model, are they completely independent, or do you use the source model then to create the target model?
What you usually do is you pre-train the source model on the source task, and then you copy it over, you copy its weights to the target, and then you optimize the target. Okay. Some of them, for example, decay, you have one model that does both domains. Because many applications you want to be good in both domains. So you can have one that then gets very good at target, but forgets the source. That's called catastrophic forgetting. Call it like that. So it's you can imagine there's all kinds of flavors here, but that's just the general idea is this. can adapt the model features so that they basically are similar for the same concept regardless of the type of the input data. What you can also do is you can adapt the inputs themselves. So you can make the image look like the target domain. And this is very often done with generative adversarial networks, or GANs. You might have heard of those already. And again, I could fill the entire lecture on how GANs work. Just very briefly, let me pick an example. Let's say we have, again, a source domain image, and we have a target domain image, and we want to make the source image look like the target image. What we first do is we have a generator. We can, for example, use a unit, which generates us an output image based on the input image, like this. And we call this a fake target because it's still supposed to be the input image, but it should look like the target image. And the way this, and we need to train that. And the way this is done is as follows. We take this fake target image and the real target image, and we feed this into what's called a discriminator. And this is just a classifier, can be a ResNet, which gives you an output real or fake. So this classifier, all this does is it has to identify, is the image real, so from the target domain, or is it fake, coming from the generator? And it learns that. And then what we do is we flip the labels and we backpropagate through and we confuse the discriminator. It's like we let the generator and the discriminator fight against each other, so they both try to outsmart each other. And this is very difficult to do. It leads to unstable training, but in the end, it can work. And it's just very short explanation of GANs. And actually, in this case, is an example from mine. It actually works surprisingly well. So on the left, we have a source image, which I don't know if you can see that, comes from a game engine, comes from Unreal. And this is by a colleague of Sarah mine, who designed a virtual African environment with animals in it. And what we did is we trained a GAN to make this look like the target image on the right, which is a real drone image. And the one in the middle is what came out. So it's not perfect. It has a lot of problems, but it looks, in terms of color and configuration, it looks a lot more like the image on the right than on the left. And why would you want to do that? Well, very simple. We know where the animals are, so we can train a detector on this. And we can draw as many images from the game engine as we want, feed them through the GAN, make them look like target, and we can train a detector which we can then apply on the target. So we could train a model that doesn't need any annotations on real data. Ideal. This worked so much, we were able to reduce the amount of labels by a third, I think, or even 50%. But we still needed some target labels because the GAN images didn't look perfect. Good. Next topic, noisy labels. Again, this could apply to some of it. So noise could be different things. It could be just an imprecise label if you have bounding box, for example, crowdsourcing, or it could be just really a downright incorrect label. Like there's one person who labeled this aardvark sand pit in the bottom right as an animal, but it obviously isn't. So if you have this and you train a model without filtering, it's just not going to perform well. The model is going to be as noisy as the data. So what can you do here? Again, number one, clean your data. If your data is noisy, you can mitigate this a little bit, but you can almost never get a perfectly working model. Only with some tricks. The best is always to pre-clean the data. But if you cannot do that, or you still have some noise, there's a couple of things you can do. Again, clean your data as much as possible. Very importantly, keep a test set that is completely noise-free. You don't want to test your model on noisy data because that is just not going to be representative. And if for the noisy training data, there's two things you can do. One, you can have a loss function that is a bit more relaxed, that is a bit more forgiving, that tries to ignore the noisy part, or you can make the model more robust so that it itself tries to be not impressed by a noisy label. Again, just two very simple things here. The list could go on and on. Many of the propositions that have been made only work on small benchmark data sets, but I've never seen them work in real life. But these are some which could work. The first one is, now we're going to go into the regression. It's what's called the smooth L1 loss, or it's also called the Huber loss. So L2, this L means is kind of the norm. So what norm you're applying. L2 is a quadratic loss. MAC loss is an L2 loss. Then if you have an absolute sum of absolute errors, the mean absolute error, for example, that's an L1 loss. And what we do here is we combine the two. So it looks like this, graphically speaking. That's the loss function. That's the Hooper loss plotted on a graph. And you can see this is a mixture of the linear and the quadratic term. And more specifically, if you look, if you are very far away from 0, it is linear. So that's just at some point it's just going to increase linearly. So basically what this means is that the prediction and the target, they completely disagree. And what we say here is not really that the model is wrong, but that the target is wrong. And but still, we don't want to eliminate this. We still want to somehow, just in case the model was wrong and the target was right, we want to penalize it. So we reduce the penalty to an absolute error, which is a lot more forgiving than the quadratic error. If you plotted a quadratic loss here at this location, it would be way off the scale. But with that, we give it a linear penalty so that the model is kind of whipped on its fingers, but not too much. Whereas if we are close to the optimum, where the loss is 0, we say that the model agrees, the label agrees, the model doesn't agree perfectly, we want to really nail it down for regression. And then we give it a quadratic penalty. And this is actually the one that is used for bounding box regression in retina. But this is something I found very useful for all sorts of regression and density estimation tasks. You might want to try it. Again, it's built into PyTorch already. It's just you don't call it MSC loss. I think it's called smooth L1 loss. That can help with noisy labels. For classification, there is something called label smoothing. I've just picked one of the earliest definitions of this. There's different ways. Before we talk about this equation, very simple in layman's terms, label smoothing means that you, again, it's a similar concept to the focal loss. When you, for example, have a label 1, you don't encourage them, you don't push the model to predict 1, but you modulate this label with the model prediction. So if the model says 0.4, then you mix that with 1 so that your target is not going to be 1, but maybe 0.6. So that you encourage the model to kind of move towards the target, but you reduce the target strength. It's kind of mixing the prediction and the target with each other. Or what you can also do, that is done here, you can mix the target label with a distribution of your expected, with the expected distribution of your classes. If you know that, for example, you have a lot of coyotes in your data set, and the target says this is absolutely not a coyote, but the model says this is one, you could mix the three together and say, okay, my target is not going to be 0 as originally, but it could be, this is with 60% probability a coyote. So you kind of encourage the model to get there, but not too much. It's a bit like that. This equation looks a bit intimidating, but it's very simple. You have Q, stripe, and P, these are the prediction and target. And H is just our loss basically here. And then what you do here is you iterate over all the K classes. And for each class, you calculate the regular cross-entropy loss. That's just built in between the prediction and the target. Then what you also do is you have an expected, in this case, predefined class distribution. This U, you can calculate this from your training sets, you can have a prior, you can do all different things. You don't even have to use the expected class distribution, you can use the model prediction as well. But in principle, you have a second cross-entropy loss here, which just tries to match the prediction with the expected distribution somehow. We can go into the paper to look in more details. The general idea is to modulate your ground truth according to a criterion like expectation, what your model predicts, etc. And this can work reasonably well sometimes, because if you do it too much, then your model is not going to learn, because if you just modulate all the ground truth so that everything becomes 0.5, the model is just going to predict 0.5 everywhere, so it's not going to learn. But you can do this a little bit so that you don't force the obviously wrong prediction, the obviously wrong classes, the obviously wrong ground truth. You don't enforce that. That's the idea here. But again, if you have noisy labels, number one, try to clean your data. Then the third concept, which isn't necessarily only for noisy labels, it can be used for domain adaptation as well, for example. Like GANs, they can be used for many other things. I'm just using them, I'm just categorizing them here. But this is a cool concept, it's called student-teacher networks. And the way it works is as follows. Let's say you have a subset of your data that you know is clean. You know there's no noise in there, or you can expect there is almost. What you can do is you can then start training, for example, a teacher network. It gives you predictions, and you train this with the clean labels. You don't have a lot of samples here, so this teacher is not going to generalize well, but it's going to be trained on exclusively clean labels. Then what you do is you take the bulk rest, the noisy data, and you train what's called obviously a student model. And the student model, of course, you train with the noisy ground truth, and this gives you a prediction. And then what you do here is you also take this noisy data and you pass it through the teacher model. You let the teacher model predict the noisy data. And this teacher model, again, it makes a different type of, the student model makes the mistakes that are expected from the noisiness. The teacher model makes the mistakes expected from the generalization problems. But these are two different scales. So what you do is you can train the student on the noisy labels, but you also train it on the teacher prediction and use that as a soft label. Then you can use what's called a knowledge distillation loss. So you literally distill the knowledge from the teacher and transfer it into the student. It's a bit actually like a PhD project. The supervisor will tell you the basics, but at some point you know your topic better. So you distill knowledge from the teacher, but you learn on something that the teacher usually doesn't see. It's exactly the same principle. And this can work wonders. This can also work for domain adaptation, by the way. But again, it's a very complicated setup. You need two different models, two different data sets, and so on. But it can work. Yeah. So noise distillation means you make the student imitate what the teacher says. But that's another approach you can use for noise distillation. And it has been used in the past. Some setups are highly specific for the data sets, but it might be worth a try, maybe beyond the summer school, because it's involved. And now we're going to go into new label training. This is becoming very esoteric, as I said. I'll just brush over it very quickly. I don't expect you to use any of that, but just so that you see what's happening. The first one is self-supervised learning. Actually, Harun is going to talk about this, right? Good. I will not go into this. I'll go into the few shot and meta learning. Just kind of this concept to see what we can do. So, what do you do if you have very few examples per class? Like, deep learning is data hungry. You need thousands of examples. What do you do if you only have 10? Well, what you can do, the first one is you can use what's called prototypical methods. And the idea here is that these classes, they all clump together in the latent feature space. So again, if you take the feature vectors before the classifier, if you have different images of cat, they should all be very similar. Because that's what the model is going to learn eventually. It learns to compress all the cats together, no matter for the cat's race or position or color or whatever. And what you can do here, what these guys have done here with prototypical networks is they learn a centroid of these features. So basically they learn to map, they average the predictions of all the cat samples they have. It's not many, but they try to clump them together and learn that and update that as they move along. And so then, yeah, is this solid squares here. They learn centroids for each class that they have on the few examples that they have. So what this works like this. Let's say you have an input image, and then you have a feature extractor, which gives you these latent features. This could be a ResNet, but except for the last layer. And then you get these feature vectors in this case. So for example, if you take a ResNet 50, you chop off the classifier, the output of that is a 2048 dimensional feature vector, which summarizes the image contents. And by default, this is trained usually, thanks to the classifier on top, to clump all the cats together. So this then gives us this could give us eventually a prediction cat if we added a classifier. And then you take a second image, you do the same, and you get another feature vector. And now again, since this also is a cat, this should be similar to the first one, right? And you do this for all the cat images, and in the end, you learn a centroid by just averaging the features as you move along. Is this. So you basically just take the mean plus feature vector. So you see here, you have the feature vector sigma, you have the feature vector sigma of x is the input, and you take the mean. Very simple. And again, because you learn this model, these feature vectors change over time as you learn, so you keep updating this. That's basically you try to make sense of what a cat looks like in latent feature space. And you do this for all the other classes as well. So then, for example, if you have a new input image that you want to predict, again, you feed it for your feature extractor. And this gives you, for example, a point here, this gray point. And you check in this latent feature space where this is. So you calculate the distances to the nearest centroids, and in this case, is the closest to guinea pig. And with this, basically, you can, if you do that well, if your few examples per class are representative, you can learn centroids, which are very good. And because of this clustering effect of the features, it also generalizes. Because it becomes difficult when you land on the cluster boundaries, but that's always a problem. So with this, you can actually try to get away with slightly better models, even if you have only few shots, few examples. These are prototypical networks. They work rather well for what's called few-shot learning. And this is now becoming a bit complicated, but again, you don't need to memorize this. It's just to show you what people have been thinking about. You can also do what's called meta-learning. Who can tell me what might be included in meta-learning? Yes.
Hyperparameters. Tune the hyperparameter.
Oh, not bad. That could be. Yes, there are meta-learning models which do that. They try to learn the hyperparameters. You can even see it more generally. What does meta-learning imply?
Like extra data about each image, like time of day, locations.
Okay, that is more related to domain shifts, maybe. It's very simple. If you think about the term meta-learning, it's learning how to learn. So these models, technically, so what meta-learning does is it trains a model, and then it observes how the model has moved, and it tries to predict that into the future. And now, how is this useful for a few examples? Let me show you. So learn how to learn. That's why it's meta-learning. It's a bit of an obscure concept which hasn't really taken off that much, but it is being studied. And sometimes it works, sometimes it doesn't, as usual. Right. So the goal is to pre-train a model so that it can adapt to new tasks with few examples. So basically, the idea is that many classes share some sort of redundancies. And if you can make, we have had this cloud before of dog, cat, and guinea pig. If we have a model that sits in the middle, we can very simply, with just a few examples, adapt into either direction. So if you suddenly have a new class called dog, and you have just 5 examples, you could very, very quickly move into that direction. That's the idea of meta-learning. And now the question is, what is a task? Because that's not a class. A task is something else. So tasks again, if you go into the literature, there is a highly complicated definition of this. I'm just gonna put it in simple words. It's something for the model to learn. So this could be classification. This could be something else. This could be detection of true, fake, true or false, or whatever, real and fake, as in GANs. Examples are subset of species. So, for example, if you have a class guinea pig, a class mountain, and a class cello, you want to learn to discriminate them. That could be a task. So you could sample this from a big data set. That's also a task. Guinea pig, mountain, and butterfly. You have 2 times the same classes in there, but it doesn't matter because it still is. You task the model to learn to discriminate these different types of images based on their category. These are tasks. So what you can do is, if you have meta learning works best if you have many species, many classes, and then you make these tasks. You randomly sample some classes, and you task the model, no pun intended, to learn to distinguish these classes. So you don't care about the classes anymore directly. You don't care if it's a guinea pig or not. All you care about is that it's a different one than mountain. It sounds a bit strange as a concept, but what you do is you just retain the fact that these classes are different from each other. And then you can shuffle their label, you can shuffle their order, but as long as you keep the classes, you keep all the images as the same, it doesn't matter. You basically ask the model to distinguish whatever currently is in a task. I told you it's gonna get weird. And so for each task, we sample n classes, here for example 3, and for each of these classes, we sample k examples. This is also called a k-shot n-way task. And we do this over and over again in training. Each time we sample random classes with n random classes with k examples for each. And then in simple terms, this is how it works. So we have a predefined number of iterations. You can say how many, like 100,000, whatever. Each time we create a task T. So we go through our data set, we sample n classes at random and k examples for each class. So today it could be guinea pig, butterfly, and mountain. Tomorrow, the next iteration, it could be guinea pig, mountain, and human. Each time you sample random classes. You shuffle the labels. So you don't shuffle across the images, but you shuffle the task labels. So in the current iteration, guinea pig might be label 0. In the next one, guinea pig might be label 3. And you don't shuffle the images, but you shuffle the class labels. So the model can't always say, yeah, class 0 is guinea pig, but it has to learn to distinguish. That's the idea. And then you split the task samples into what's called a meta train and a meta test set. So you take your k examples and you say, if k is 10, I'm going to use the first 5 for training and the second 5 for testing in quote marks. We do a split in this task. And then you have what's called an inner loop, where you train on the meta train set. So you train the model based on the current class labels, which are shuffled, to predict, to learn how to basically learn to predict. And you keep the gradients. So I told you in the beginning, in the previous lecture, you can specify to keep gradients, and with that, you just keep them in memory. So at some point, the model has trained all these meta train sets to, at this moment, assign that, for example, one is these 5 guinea pig examples are 1. These 5 mountain examples are 0. And then you evaluate your model on the meta test set, which still have the same. 1 is still guinea pig, 5 is still mountain, or whatever it is. And you evaluate the current model on this test set. And again, you keep the gradients. Then you do what's called an outer loop, where you perform a meta gradient descent. So you basically first you train the model on this meta train set. You evaluate it on the meta test set and look and see how far off is the model. So you use the test set, basically the meta test set, to calculate the gradients, and then you update at the end, so that you can kind of learn in which direction the model has to go to generalize. it's quite complicated. Maybe this illustration helps a bit. You see, probably not as well. So you have in this case 3 tasks. You have a starting point, and you learn in which way to go with the meta train set. You check where it has to go with the meta test set, and you move the model. You average, and then you do that again. Meta train set. You learn where it has to go. Meta test set. You average the gradients. You go there. So at some point, the model is going to be in the middle of these 3 circles, each of which are tasks. And with that, it takes less steps to adapt to each task. And with that, it can adapt to each label class or species that you have very quickly. That's the general idea of this. I told you it's very esoteric. Sometimes it works, sometimes it doesn't. But the idea is then these 3 tasks, they can again be our dog, cat, or guinea pigs. So if the model sits somewhere in between these clusters, it doesn't take many gradient steps. It doesn't take many examples to move into either direction. Then you just need a few from each class, and you can make the model move there. So I'm not expecting anyone to use that because it takes a while to understand, and it only works on very small models. But it's just kind of as a bit of an outlook of what people have been trying to do in machine learning. Let's sum this up very quickly. So again, and how this is going to be useful for you. Class imbalance. Loss rating and custom losses can help a little bit. Curriculum learning, I found, can help either a lot or it can cause massive overfitting. I don't know what's going to happen if you use it. Domain adaptation. Adapting the features either helps a lot or not at all. I found the domains need to be similar, otherwise it doesn't really work. Adapting inputs is difficult. GANs are notoriously hard to train. If you really want to go down that avenue, use pigs for pigs, pigs to pigs, or CycleGAN, which are 2 GAN architectures which generally work remarkably well. Let me know if you want to do that, and I can point you to some resources. But generally, if you have domain shifts and you have labels, use those. Do fine tuning. It works best. Noisy labels. Again, label solving can help a little bit, but if the noise is too much, it doesn't help. If you have more noise than data, no model will ever be able to recover. Student teacher is a really cool concept I found, and it's also good for other stuff like domain adaptation. Again, it's hard to set up, a little bit harder, and it won't always work. And then very few labels. So self-supervised learning, it works really well on stuff like ImageNet. It works quite nicely on remote sensing, people have shown. I found it for very cryptic problems like aerial wildlife detection is virtually useless. It's not like there is the self-supervised learning. There's infinite ways of doing this, and the difficulty lies in how to design the self-supervised learning procedure. We're going to see that on Friday. Few-shot learning. I found this to mostly work on benchmark data sets, but I might be wrong here. Meta learning, don't bother. I just wanted to show you as a bit of an outlook. And I guess that's it. That's the take-home message. Curate your data set. It's what Tanya said, garbage in, garbage out. You cannot recover it in the model. Everything else is a hack. And with that, I think you're all hungry, so ich habe fertig. I'm done here. So, yeah. See you all.